Hello and welcome back. So we are continuing with our lectures on convolution, and we'll start by talking about what's called periodic convolution. And so this means convolution for signals that are periodic. Well, we haven't talked about periodic signals yet. We're going to talk about them in some detail when we talk about things Fourier in the future. But the notion is not complicated. So let me just quickly sort of review all the things that we want to say about periodic signals so that we have them in our bag for use today and for use in the future. Okay. So we're going to let T be a time domain, and it's either, so periodic signals for, it to make the most sense need to be, have a time domain that's unbounded above and below. All right, so we're going to consider this in the discrete time case and this in the continuous time case. Right, so a signal, and I'm not necessarily going to put any properties on this at the moment, so let me just say f in f to the t. Okay, so this is a perfectly sensible thing when in the discrete time case, but in the continuous time case, of course, this is not a space of signals that's necessarily of any use. So, but for the purposes of this definition, it's okay. So a signal like this is periodic with period t if f of t plus t is f of t for all t's. Okay. So some elementary observations about periodicity. So if we're in the discrete time case, then the period has to be a discrete time as well. Okay. So in other words, the period has to be an integer multiple of delta, of course. Okay. It's possible. So a signal of period t, so periodic with period t is what I mean by that, is also of period kt for any positive integer k, and that just follows immediately from the definition. Okay, and so the smallest period is often taken as the period. Okay, so I'll say more about this. And so, if you're periodic with some period t, then you're periodic with every integer multiple of t. And so you might ask for the inf over all t's, for which that's true for your signal f, and then you call that the period. That isn't necessarily a useful thing to do. So there are periodic signals with no smallest period. And so for such signals, it's not really possible to talk about the period. And it's clear what those things are if you think about it for a second. These are the constant signals. Okay, so no matter how you choose t, they'll be periodic with period t. So those things don't really have a well-defined smallest period. But you know, for other periodic signals, you do have a well-defined smallest period. And when you say something's periodic, often that's what you mean. But actually, for us, as we'll see later today, we're going to be fixing a t. Okay, and then talking about spaces of signals with that period. And so it's possible that you could have signals with that period that have a smaller period. Okay, so that have a period which is t over k for some k, or which don't have a smallest period. All right, so that's how we're going to be approaching this typically, is by fixing a period and then talking about signals with that period. Okay, just like we have spaces of signals, we also have spaces of periodic signals. Okay, and then, so for example, if k is a non-negative integer, then ck per t okay, so this denotes the t periodic signals in ck. And there's nothing sort of preventing you from talking about infinitely differentiable ones as well. Okay. All right. Okay, so it's important to notice here. So when something's periodic, very often you restrict its consideration to a period. Okay, and we will typically think about the period from 0 to capital T, right? And then you just sort of focus attention on looking at the signal between 0 and capital T, and because the signal's periodic, that's enough to do what you want to do. However, with respect to this definition, there's a little thing you have to be aware of, and that is when I write ck here, I mean ck on all of R. Okay, and so for example, so let me just sort of draw the kind of thing that I'm thinking of there. So let's say we're going to fix a period t, like so, and we're going to talk about, just for limited by my ability to reliably draw things, let's talk about C0 per T of R. Yeah. Okay. All right, so as I say, you normally fix your attention to a period, like so, okay? And so this signal, okay, is not going to be in C0 per, and the reason is because it's periodic, the value there gets picked up here, and you go along like so, and so you're not periodic at the endpoints here. Okay, so that's what I mean when I say the CK here applies to R, not to a period. Okay, and so what you would need is you would need for the to be in C0 per, you need for the values to match up at the endpoints. Okay, so you need for a signal that kind of looks like that. Okay, so the values match up there, and so that when you draw the next period, it's continuous at that point. Okay, so that's something to be aware of always when talking about things that are in these classes, is that I mean the regularity applies to the function on all of R, not just on a single period. Okay, which isn't the case for this class of signals. Oh, so maybe let me sort of say here. So we've been talking about spaces of signals with norms, and so the space C0 per T is a Banach space. With the norm, and of course it's the usual norm that you use for things that are continuous. And to calculate the norm, of course, you don't take the sup over all of R. You take the sup over a period, and for things which are in C0 per, of course, that's the same. But when we talk about the other Banach spaces of periodic signals, you'll see why it's important to restrict to a period. So we may as well do it here as well. Like so. Okay. All right, and the proof of this is, so we've already seen that if you take something that's in C0 on this compact interval, then if you take a Cauchy sequence in there, those will converge to something in C0, and so the only thing you need to verify is the periodicity of the limit of the Cauchy sequence, but that's easy. Okay, so that's spaces that are regular, continuous, or of some higher order differentiability. Then you have the LP spaces that are periodic. Okay, so for P in 1 to infinity, and we'll include infinity here, we have LP per T of R F. Okay, so it's important to notice here that in both these cases, right, I had the domain as being R. Sometimes people will put the domain in a case like this as being like so, and the two things are equivalent. Again, there's some fussing around it, and especially you see here with the endpoints, whether I should really be talking about this, and I'm not going to fuss very much about that. Okay, but for our purposes, we're going to think about periodic things as being defined on all of R. All right. Okay, so LP per is F's from R to F, such that F restricted to 0T is in LP 0T. Okay, and so on each period, you're in LP. Okay, and so, again, it doesn't matter if you, in these cases, if you include the endpoint, and then, in the, as I've already talked about, in the case of C0 or higher regularity, at the endpoints, you do have to worry about this, but in LP, it doesn't matter. Okay, and the norm, so these are Banach spaces. With norms. So I take F, which is an LP per, and I calculate its P norm. This is just going to be the P norm in the sense that we've talked about before of F restricted to a period. Let's say the period from 0 to T. Okay. All right. Now there's an annoying little point here, and that has to do with the fact that things in LP are not signals, but equivalence classes of signals, with equivalence being that the two signals agree almost everywhere. Okay. So, there's messing around that you have to do. Do you ask, what's the equivalence relation in here going to be? Is it going to be agreement almost everywhere on R, or is it going to be agreement almost everywhere on a single period? And then you ask for that to hold. Because the signal is periodic, it will then also hold on R. So there's messing around that you can do here with this fussing with whether you're talking about signals or equivalence classes of signals. But the fact is that it doesn't matter whether you take agreement almost everywhere on R or agreement almost everywhere on a period. For the purposes of talking about LP, and so, for example, the norms, it doesn't matter. Okay, so the point is, you can assume without loss of generality that your signals, your equivalence classes agree almost everywhere on T, and then they're extended to have that same property on every other sort of fundamental period, say from 2T to 3T, from 3T to 4T, and so on, just by taking F and translating it so it's periodic. Okay, so whether it's agreement almost everywhere here or here, the fact is it doesn't matter. Okay. Okay. Good. Sorry, I also need to talk about the discrete time signals as well. And so the discrete time signals are the little, they would be the little LP spaces. But the thing to keep in mind is that because we're talking about periodic things, in the discrete time case, okay, the dimension of all T periodic signals is finite. Okay, now that's, if you think about it for a second, that's fairly clear. And it's just really because of periodicity, you only need to know the value of the signals for in a single period. Again, let's say from 0 to T. And in the discrete time case, there's only going to be finitely many times, let's say between 0 and T. And so a basis for these is, and so again, I'm going to draw the basis rather than write a formula for it. Okay. Right. Okay, so I'm periodic with period t. Okay, so let's say here's a period, and here's another period. And of course, I also go off to minus infinity as well, but let me just draw the positive periods for concreteness. Okay, so the first basis vector in this space of periodic signals is going to be the one that is 0, except at 0, at t, 2t, 3t, and so on. Okay, and then it's 0 everywhere else. Okay, then the next one, so let me, okay, so the next one will be 1 at the point delta. Okay, so if this is 0, that's delta, and then t plus delta. Okay, and then it's similar, and then you can see how this goes now. Okay. So this one will be 0 everywhere except at 2 delta and t plus 2 delta, and so on. Okay, so you just sort of take this one and then you shift it to the right by delta, and then 2 delta, and then 3 delta, and then eventually you end up back where you started, and then that gets you your basis. Okay, so you can see why you have the finite dimensionality, because there'll be one basis vector corresponding to those points. Okay, good. And so therefore, we don't need to distinguish between little l per, right, the periodic signals, because they're all just the same space. They're all just the space of all discrete time periodic signals. And so we will denote, oops. Okay. So we will denote, again, just to keep the notation kind of consistent, we'll denote by L per T of Z of delta the space of T periodic. Signals. Okay, and the point is we don't need a P there or anything like that, because all of these spaces are the same, and because they are finite dimensional, it doesn't matter which norm we use. So we can use whatever norm we want. Okay. All right, so that's periodic signals. We're, like I said, we're going to look at these in some detail when we talk about Fourier things, and so we're going to be especially interested in these spaces for p equals 1 and 2. Okay. All right, so that's that. Now let's talk about what we came here to talk about, which is periodic convolution. Okay, so periodic convolution comes in 2 flavors, just like the normal convolution, not periodic convolution, a discrete and continuous time, and there's formulas for them, and I'll just sort of write the formulas down. Okay, so in the continuous time case, the formula for the convolution is f star g, and the formula looks rather the same as the in the aperiodic case. So it's f, so this is t, is f of t minus s G of S ds. Okay. And in the discrete time case, it's F star G of K delta is, and so you replace the integral with a sum as usual. Okay, but the sum now goes from not from minus infinity to infinity, just like the integral here doesn't go from minus infinity to infinity, it goes from over, you integrate over a period. Here you sum over a period, and that means going from, say, 0 to n minus 1. Okay, and I'll tell you what n is here in a second. Okay, and so it's F of K delta minus J delta G of J. Okay, and T here is equal to N delta. Okay, so that's the period in that case. All right. And so, you should check that that all makes sense. So first of all, you can easily verify but by the periodicity of F that this thing will indeed be periodic, and similarly here. Okay. In fact, the entire integrand here, or entire summand here, will also be periodic. Okay, and so really this is just restricting the convolution to a single period is the point. Okay, now, of course, you need to talk about convolvability still in this case. Okay. All right, so let's talk about continuous time. Periodic convolution. All right. Okay. So the story here is quite similar to aperiodic convolution, but there are some important differences. Okay. So let's first talk about convolvability. And so what do we need for convolvability? You need to be able to, F and G need to be such that you can do that integral. Okay. And just like in the aperiodic case, what this means is that there's going to be conditions on F and G, which ensure that you have convolvability. Okay, and we'll talk about those, and they look rather similar to the conditions we had in the aperiodic case. Okay, but like I said, there's a few differences, so I want to be careful about just a little bit. Okay, so we denote, just like in the continuous time case, we denote D of Fg to be the T's in R, such that F of T minus S, G of S. Okay, so we want to think of that as being a function of S. Okay. And so, sorry, this is a function of S, and we want this thing to be in L1 of period. Like so, okay? All right, so as a function of S, it's in L1, but only, of course, over a period, whereas of course, in the aperiodic case, we asked for it to be in L1 of all of R. Okay, then we say that Fg is convolvable if D of Fg has measure 0. Okay, so that means that I can do that integral for almost every t. Okay. All right, and then of course, you know, and the convolution or you know, maybe I'll say the T periodic convolution of F and G is just given by the formula above. And you know, again, you want to fuss with for the purposes of having a precise definition with you know, D a little bit. Okay, so it's F of T S G of S ds when T is in here. And again, it doesn't really matter what you take it to be for otherwise, because it's just a set of measure 0. Okay. All right. And so then you have a theory of convolvable pairs. Okay. And as I said, the theory looks rather like it does in the aperiodic case, and there's really only one slightly interesting difference that I'll draw attention to, and otherwise I'm just kind of vaguely say that it looks just the same as it does in the aperiodic case. Okay, so we have some special convolvable pairs. Okay, so let's list those. Okay, so the first case is when F and G are in L1 per T of F. Okay. All right, so in that case, they're convolvable. Okay, so I'm giving you pairs of convolvable signals. So as long as F and G are in L1, then they're convolvable. And just as in the aperiodic case, the convolution is in L1. Okay. And you have, we have the same algebraic structure as for L1 with one exception. You have associativity of the convolution product. Okay, and so essentially we're talking about signals with a bounded domain here, and that's enough to force associativity of the product in this case. Okay. Okay. All right. And so what are those usual algebraic structures? Well, I'll just say them in words. I won't write them down. So it's the product, convolution product is commutative. So FG is convolvable, then GF is convolvable, and F star G is equal to G star F. It's linear. Okay. And there's no unit. All right. And it's also the case that you have that it's not an integral domain. Okay, so you have non-zero f's and g's for which their convolution is equal to 0. Okay, so except for this, it has the same algebraic structure as the other case. Okay, and it also has a continuity condition given by some norm bounds for the convolution, and they're very simple. Sorry, less than or equal to, like so. Okay. All right, so that's the L1 case. Then you have this other case, which comes from what was Young's inequality. Okay. And so then remember that we have F in LP per T. Okay, and so it works exactly the same as the point as the aperiodic case, at least in symbols. All right. Okay, and then we had the special cases. Okay, of all right. So there was two cases that I drew attention to before, and I'm not going to write them down because the consequences are the same as they were in the aperiodic case. All right. So the first case is where P is P, and Q is the conjugate index of P. Okay, so what that means is that 1 over P plus 1 over Q is equal to 1. Okay, so that cancels with that one, and therefore it implies that R has to be equal to infinity. Okay, so this is true in that case, but there's an extra thing that's also true. And so when P is P and Q is P prime, then the convolution is not just in L infinity, but it's in C0. Okay, so that was true in the L1 case, in the aperiodic case, and it's also true in the periodic case. All right. Okay, and you also have a norm bound. Okay. Okay. All right. Okay, so up to me sort of writing down repetitively all the things I already wrote down for the in the aperiodic case. That's continuous time periodic convolution. All right. Then there's discrete time periodic convolution, which is dull. Okay, and the reason, of course, that it's dull is everything's finite dimensional in this case, as I observed for discrete time periodic signals above, that the space of all those things is finite dimensional, and so every pair F G is convolvable. Okay, and we have a continuity in any norms we choose. Okay. Just because in finite dimensions, all norms are equivalent. And so, when you write down a condition like this and you make a choice of norm here, if you change those norms in any way you want, all that you're going to change is you might put a constant there. Okay, but you'll still get a continuity condition that looks like that. You'll have maybe, some norm 1, norm 2, and norm 3 for your spaces, and it just totally doesn't matter. They don't even have to be p norms. They can be any norm that you like, right? So, so there's not much interesting to say in the discrete time case. Okay. All right. So that is periodic convolution, right? And so as I said, that's going to show up in a prominent way when we talk about Fourier things. Okay, so we're going to see convolution shows up in kind of very surprising ways when we talk about things Fourier. Okay, but we'll get there. All right. So now is something. As Monty Python would say, now for something completely different. So I'm going to talk about convolution distributions, and I'm going to do it in far more generality here in these, sort of more or less informal and unobserved online lectures in far more detail than still not in a lot of detail, but in far more detail than I did when I taught the course. Okay, and the reason I want to do that is because it's hard to find this approach sort of outlined systematically anywhere. So I want to try and do that here. Right, so I want to give you the main idea of how this works, and it'll take some time, and there's going to be a lot of stuff that you have to do. But at the end of the day, you get a theory that's quite satisfactory. And if you kind of try to take a streamlined approach to talking about convolution of distributions, you end up with something that isn't quite as satisfactory at the end of the day. So I think in a little bit more generality, you end up with something that's quite beautiful. And it is as powerful as the theory for convolution of signals itself. And again, if you take a more streamlined approach to convolution of distributions, you don't even get that. You don't get a theory that really generalizes the normal theory of convolution for signals. So the objective is to develop a theory which includes the convolution of ordinary signals as a special case. Okay, and it turns out to do that requires a bit of buildup. Okay, and so the first thing you have to do is you have to talk about new classes of distributions. Okay. So we've talked about distributions, and when we talked about distributions, we talked about these and their topological dual. Okay, now it's a very common thing when making use of distribution theory to not just work with D and D prime. Sometimes you want to work with different kinds of test signals, which give you different kinds of distributions, because the way that you're using distribution theory, it either makes it not convenient to work with this pair, or maybe even impossible to work with this pair, and you are forced by the problem to introduce new spaces of distributions. Okay, and we will see a very concrete realization of that when we talk about Fourier transforms of distributions. And the issue that's going to show up is that when you take the Fourier transform of distribution, you don't get a distribution back. You get a different kind of an object, which is a different kind of distribution, right? Okay, so, but for our purposes, we're talking here now about convolution, right? And there's, for the purposes of talking about convolution, I'm going to introduce two new classes of test signals, okay, and their corresponding duals. Okay, and let's talk about the space of what's called what I'll call bounded test signals. Okay, and so I'm going to call these B sub 0 of RF. Okay, and this is going to be okay. So they're going to have the following properties. So first, F is going to be, as was the case with D, and normally when you introduce classes of distributions, you normally are going to ask that the test signals for that class of distributions be infinitely differentiable. And the reason, just like it was in the D and D prime case, is that you want to be able to differentiate distributions freely. Okay, so we're going to ask that these be infinitely differentiable. And we're going to ask that F and all of its derivatives be in C0. Okay, so remember that this means that that they converge to 0 at infinity. Okay, you know, the 0 here is just going along for the ride because I already know that they're infinitely differentiable. And so certainly the kth derivative will be continuous, right? So that the substance is that part, not that part. Okay. All right, so what's, and so when we talked about D, okay, so we defined the space D, but really one of the most important things about D is not the space itself, but also the convergence that we define in D, and the same thing we need to do here, okay? So we define a topology in B0 by specifying convergent sequences, just like we did in D. And again, you know, you need to prove that that's a meaningful thing to do, and other people have done that. Thank you. Okay, so we say then the sequence, let's say phi j in B0 converges to phi in B0 if the sequence of derivatives, the jth derivatives, oh, sorry, kth derivatives, converges uniformly to the kth derivative of phi. Okay, and this has to hold for every non-negative k. All right, so we have, and so it's not as intricate as convergence in D, where we, apart from, we had this same condition in D, which is that the sequence of derivatives converges uniformly to the derivative. Okay, but we also required that there be a common compact support for all of these things when we talked about convergence in D. And the reason that we did that was because in D, we wanted to be able to include all, as special cases, all locally integrable signals. Okay, and so that forced us to have a notion of convergence in D like we did. Okay, here we have a different objective, and we require, therefore, a different kind of convergence. And the convergence, like I said, is uniform convergence of all derivatives on all of R. Okay. All right, and there's lots of stuff to do here if you want to get in and really understand what's going on here. So, for example, there's notions of completeness and Cauchy sequences that you can talk about here, right? So to develop a coherent mathematical theory of all of this requires going beyond what I'm going to show you here. All right, okay. So what properties does sorry, then I apologize. So the final thing you need to do here, of course, is we have this space of test signals. We have a topology on it defined by specifying its convergent sequences. So then you can talk about continuity. Okay, so you can talk about continuous functions to and from B0. Okay, and so we're going to talk about continuous linear mappings from B0 into F, just like we did when we went from D to D prime. All right, so D prime was the set of linear continuous functions on D. Okay, so the same thing is going to be true here. Okay, so the space, all right, and so the space here we denote by, so it's D prime. So the notation's kind of funny here because here it was D and D prime, and here it's not. Okay, the space D prime L1 of R F is the set of linear, continuous, linear mappings theta from B0 to F. Okay, and so continuity means just what you expect it to mean. So thus, theta is linear, and the numerical sequence theta applied to phi j converges to 0 for every sequence phi j in B0 that converges to 0. Okay, so the definition in words is exactly the same as our definition of D prime. The only thing that changes is the meaning of that, right? So the convergence to 0 is not in D, but it's in this new space that we introduced, B0. Okay. Other than that, the definition is structurally the same as The same as it is for distributions. Okay, continuous linear functions, and it's the meaning of the word continuous that you have to think about here. Okay, all right. So examples. So sorry, maybe let me do it this way. So okay. Oh, and so we call d prime L1 is what are called space of integrable distributions. That's the name you give to these. The special class of distributions is called integrable distributions. Okay. So first of all, D, of course, is contained in B0. Okay. And the inclusion is strict. You certainly expect it to be. The condition for membership in B0 is a lot weaker than the condition for membership in D. We only require here that our signals and all of their derivatives go to 0 at infinity, whereas in D they had to have compact support. Okay. And as an example of something which is in B0 but not in D, this signal is in B0, but not in D. Okay, so you can check that the derivative of this goes, first of all this is infinitely differentiable. All derivatives exist and are continuous, and also all derivatives go to 0 at infinity. Okay. All right. Okay, so one of the consequences of this is, so you kind of imagine just symbolically that so D prime is the dual of D, and D prime L1 is the dual of this, and because this space is smaller, okay, and distributions are continuous linear functions on this space. So if you have a continuous linear function on a smaller set of signals, you expect there to be more continuous functions. Okay, so in other words, you expect the duality here to reverse the inclusion. Okay, and that's true, all right, but it doesn't just follow just like that. Okay, this makes it sensible, but not necessarily true, that D prime L1 of R F is contained in D prime of R F. Okay. Okay, so this is not just sensible, it's also true. Okay. And moreover, the inclusion of D prime L1 R F in D prime F is continuous. Okay. All right. So and so I apologize. I haven't told you yet how to make sense of this statement. Okay, but it has the obvious meaning. Okay, so how do you define? So for continuity, we have a topology here described by telling what the convergent sequences here are. Well, what are the convergent sequences here? Well, they're defined in exactly the same way as we did for D prime, and that is to say, we use pointwise convergence. Okay, so you fix a test signal in B0, then you take a sequence in here and you evaluate the sequence on the test signal, and that numerical sequence should converge, right? So the notion of sequence, and this is the common thing for spaces of distributions, is the topology that you use is this weak topology that we talked about, or the pointwise convergence topology. Okay. So that's what the convergence there is, and so then continuity here means that a converging sequence here maps to a converging sequence here. Okay. All right. Now, some other properties. So when we designed this space, one of the things that we wanted to get out of this was we wanted all locally integrable signals to have a representation as a distribution. Right now, what about this one? Well, that kind of suggests what we're going to go for there. All right, and remember that to include a function, so I'm not talking precisely here, but this is a general observation about how if somebody gives you a new space of distributions, as I've done here, and you want to say what an important way to understand what that space of distributions is to ask exactly what are the normal functions which have representations as distributions in this new space that you've given me. Okay, and the way to think about that is okay. So what are the conditions on F, a normal signal F, so that theta F is in D prime O1. Okay, so we know that if F is locally integrable, then it gives you something in here. Okay, so then the question I'm asking is, when is that something in here? In here. Okay, this requires that for any phi, now you take phi to be in the space of test signals for the distribution space you're talking about, and for us that's B0. Okay, the integral theta F of phi, and so now I'm being a little bit vague here. Must exist. Okay, and not only must it exist, but it should have some other properties. But let's first of all just talk about the well-definedness of this, alleged new object theta F. Okay, so if I'm going to define theta F, and I haven't done that yet, this is how you're going to define it. Okay, so it needs to be defined in exactly the same way as we took a locally integrable signal and defined something in D prime. We did that by exactly this formula, and so as I'm trying to, in a very roundabout and convoluted way, describe, is that if I give you any class of test signals, like this one, if you want to ask what functions are in there, the thing to ask is about the existence of that integral. Okay. All right, so now let's think about that. So we have a phi, which is in here. Okay, now the existence of this integral doesn't really care about the fact that phi is infinitely differentiable, right? It's only the values of phi that I'm concerned about. So, it's the continuity of phi that matters here. And all I know about phi is that it goes to 0 at infinity. Okay, and I don't necessarily know how fast it goes to 0 at infinity, but it goes to 0 at infinity. So, this is like the space, of course, like that. Okay. Now, if I'm going to take any phi and I want to make sure that f, when I pair it with phi, has an integral, really the only thing that's useful about phi, because its decay at infinity may be quite slow, the only thing that's really useful about a phi like this is that it's bounded. Okay, so things in C00, C00 of RF, those are bounded. Okay, and so it's really the boundedness that I get to use here. Okay, and so what this really requires of f is that f be integrable. Okay, because I'm going to take the integral of f times some bounded thing, and so that will certainly be integrable, because the norm of this is going to be less than or equal to the norm of f1. Okay. All right, and so the point is that the conditions are that f should be an L1. Okay. Not L1 loc, but L1. Okay, and that's why these are called integrable distributions, and it's because they generalize integrable signals. Okay. All right. Now, there's another characterization of integrable distributions that's actually going to be useful for us. And this sort of involves knowing something more about integrable distributions than we're going to be able to talk about in any detail here. Okay. All right, so so it turns out that continuity of the way we defined this space DL1, okay, is that it's continuous linear mappings on this space, okay? So, and then we had a notion of topology on here, okay, defined by this uniform convergence like this, okay? All right, now what we're going to do is we're going to say that to characterize something which is in D prime L1, we don't have to, we can restrict our converging sequences, okay, to a very special class of converging sequences. And these are what I'm going to call special approximate units, okay? So let me tell you what those are. Okay, so these are going to be functions that converge to 1, the function 1 defined on all of R in a certain sort of a way, okay? All right, so a special approximate unit is a sequence I'm going to call these psi j in D. Okay, so these are infinitely differentiable with compact support, but the convergence is not going to be in D, as we'll see. Okay, so it should satisfy some conditions. Okay, so first, there should be a uniform boundedness condition on the derivatives of the terms in the sequence psi j. Okay, so for each r, there exists a positive number mr such that the infinity norm of psi j, rth derivative, okay, is less than or equal to mr, and this is true for every j. Okay, so this means that the rth derivatives of the terms in the sequence are uniformly, okay, so independently of j, uniformly bounded by some number. R is allowed to, this bound is allowed to depend on r. So you change r, then this bound can change. All right, so it's not uniform in r, it's uniform in j. Okay. And then the important condition here is that it converges to 1, okay? And it converges to 1 in a very strong way, okay? So for any compact K, and you should think in your mind K to be, say, minus T to T. Okay. There exists an N such that psi j restricted to K is equal to 1. Okay, so that means it's exactly 1 on K for all large enough J's. Okay, all right, so it doesn't just get close to 1 on the compact set K, it's exactly equal to 1. And in your mind, the way you should picture one of these special approximate units, okay, so this is a sequence, is like this. Okay, so let's say I have -1 to 1, 2, -2, and so on, okay? And so sorry. Okay, so on the interval from -1 to 1, I require psi 1 to be identically equal to 1. But it has to be in D, right? So my sequence is in D. And so I just kind of chop it off, and I might do it. So it doesn't matter if you do it exactly like this, but here's one way to do it. Okay. And then psi 2, which I'll draw in blue. Okay, so psi 2 would be identically 1 from -2 to 2. And again, it has to be in D, so I'm going to do this to it. Right. And, if you choose to sort of, cut these things off outside the interval that you're talking about in the same way. Okay, so in other words, you've just taken, so this chunk is the same as that chunk just shifted, then you'll be sure to satisfy condition A, and the sequence is obviously constructed to satisfy condition B. And so this is kind of your prototypical special approximate unit. Okay. All right, and so, it's called an approximate unit because of its convergence to the function 1. All right, so then what you can prove you can prove that theta in d prime. Okay, so you take some theta, which is already in d prime, and the thing that you want to know is whether it's in this space. Okay, so I know that this space sits inside d prime, and so what I'm trying to do is I'm trying to give a condition which identifies which of these are in here. Okay. All right, so we can prove that theta is in d prime if and only if the numerical sequence theta of psi j converges, doesn't matter to what, just converges for every special approximate unit psi j. Okay. All right, so this is, and for us, this will be the most useful because we're going to remember our objective here is to talk about convolution of distributions, and it's this property that's going to be the one that we're going to make use of. Okay. All right, so that defines for us a new class of distributions. What these so-called integrable distributions. Okay. All right, so there's another class of distributions that have particularly nice properties with respect to convolution of distributions, and those are called distributions with compact support. Okay. All right, so so this is the distribution space DL1 corresponding to the test signals B0. Okay. Now consider, this is a new class of distributions. The space, and I'm going to call this, as everybody does, script E of signals in C infinity of R. Right, no other conditions. Okay. All right, so E is just some distribution-y notation for this space. Okay. All right, so when I talked about D, right, I required that they be in here, but that they have compact support. And when I talked about B0, I required that they be in here. And that they go to 0 at infinity along with all of their derivatives. Okay, so E is just going to be this space with no additional restrictions. Okay, so then as with the other spaces, the important thing is, what does convergence here mean? Okay, so a sequence phi j converges to so a sequence in E converges to phi in E. Okay, if for each compact K in R, the sequence, so for each compact K in R, and for each K non-negative integer, the sequence of kth derivatives of this sequence. Oh, sorry, not the. Okay, the sequence of kth derivatives restricted to K converges to phi restricted to K. Okay, so that's the notion of convergence in E. Okay. This is a classical kind of a topology that's often used in many areas of mathematics to do all kinds of different things with the space of infinitely differentiable functions. Okay, and here we're using it to talk about distribution theory. Okay, so the space E prime is the set of continuous linear mappings theta from E Okay, and so continuity here has the definition of continuity that you always use when you're talking about distributions, and that is that if you have a sequence in here that converges to 0, okay, by this mode of convergence that we just defined, then the resulting numerical sequence theta evaluated on the terms in that sequence should converge to the number 0. And so it's the same notion of continuity that we've had in every case, and it's the same for all distribution spaces. Okay, so again, this is the notion of the weak or pointwise convergence topology. Okay. All right. So properties. So these are these have a name, just like D prime are distributions, and D prime L1 are integrable distributions. So these are distributions with compact support. It's the name you give to these. So it better be the case that these are distributions with compact support in the normal sense of the word, and of course they are. And so theta in, so first let me do this. Okay, so first we notice that as with integrable distributions, we have an inclusion of the test signals from D in this new class of test signals. So this is typically going to be the smallest class of test signals, and so they're going to be included in all the other ones. That's not exactly true. We're going to see one important class which doesn't include these, but many of them, it's the case that D is contained in whatever the new class of test signals you're talking about, and that's true here too. And so what I just said is that D of R F is contained in, and of course it's not equal to E of R F. Okay, and of course there's lots of examples of things in here which are not in here. just take, for example, the function phi of t equals t, right? So it's certainly infinitely differentiable, but it obviously doesn't have compact support. So it is sensible. Okay, so when you take duals, that the duals should reverse the inclusion. And again, it's because you're requiring here continuity on a smaller collection of functions. And so continuity on a smaller collection of functions should lead to a larger number of continuous things. Okay, so it's sensible that E prime should be contained in okay, so this is true. And moreover, theta in d prime. All right, so again, what we want to do is we want to give a condition that identifies those distributions which are in E prime. Okay, and the name suggests that either the person who named it isn't very smart, or that a distribution in here is in here if and only if it has compact support. And of course, it's the second thing. Okay. Okay, so the space E prime is in name distributions with compact support, and in fact, it's distributions with compact support. Okay. Now, again, let's have this exercise of trying to figure out what are the conditions on an ordinary signal f, so that theta f will be in E prime. Okay. All right. So again, this is how you determine whether, for a new class of test signals, which functions have the property that theta f is in this new space of distributions corresponding to the test signals. And in this case, it's E and D prime. Okay. So all I know about phi here is that it's infinitely differentiable. So this is now going to place super strong conditions on f in order to ensure that this integral exists for any infinitely differentiable function phi. And you can convince yourself relatively easily that this is going to require that f itself have compact support, and that on its support that it be integrable. Okay. So you can see that easily enough, and you can prove it as well. Oh, and so here, let me write this down, and then I forgot to mention something above that I'll mention here. Okay, so one can convince one's self, that F must vanish almost everywhere outside some compact interval S, and that F restricted to S is in L1 of that interval. Okay, so you can convince yourself that that's the natural thing, and then you can prove that. Okay. And so the thing that you want to prove here, and so maybe, sorry, let me go above here and mention it in the case that I forgot to mention it in the first case. So here we said that for integrable distributions, the natural class of locally integrable functions to work with are those that are integrable. They're in L1, okay? And then the thing I forgot to say is that, so you have an inclusion of L1 in D prime L1, and that inclusion is continuous, right? So if you take a sequence that converges to 0 in the L1 norm, okay, then the corresponding sequence will converge to 0 in D prime L1, okay? And the same thing happens here, okay? That if you take a sequence, if you fix an S, and you take a sequence that converges to 0 in L1, then the corresponding sequence in E prime will converge to 0. And of course, as I said, the notion of convergence in E prime that you use is weak convergence. Okay, good. So that makes me think that I said something's wrong here when I talked about convergence here. I think I talked about weak convergence here, and I didn't mean to do that. In any case, maybe I did that, but incorrectly. Okay. All right. So these are now two new classes of test signals. E prime, sorry, new classes of distributions, E prime and DL1 prime. I'm not so clear now why these are interesting to me, but next time we'll see how these are, well, first of all, D prime L1 is going to be used to define convolution between distributions after a bunch of other constructions, all right? So it's not just an immediate thing, you have to still do some work. And then an important class of distributions for which convolution makes sense, so that involve convolvability of distributions, are going to be those with compact support. Okay, but that's going to be what occupies us next time.